Hello everyone, this is Dr. Webb. When you took calculus, before that, you spent years and years, working on algebra, pre-calculus. All of this, for a very large degree, was working on manipulations of numbers and single variables. And you needed all of these tools from that to be able to go and do calculus in one dimension, which is what you focused in on, especially in Calc 1. So we need those same sort of tools, but now we need them in higher dimensions. And so this first part of the course, really, we're going to be focusing in on what's called analytic geometry, which is where we're trying to build the same sort of algebraic tools that we had in one dimension for Calc 1 to be able to do calculus in higher dimensions. And so, for higher dimensions, what were numbers is going to transition into what are called vectors. So what is a vector? So a vector is a mathematical object with a direction and a magnitude. So often we represent vectors as sort of a straight line, so that gives it a magnitude, and then we want a specific direction on it, and so we put a little arrow pointing which way it's going. Right, so a vector has magnitude, so magnitude is talking about length, and it has direction, and that's saying that it's going somewhere, or pointing in some way. Okay. So if you think about regular numbers in one dimension, really we can think about those as vectors as well. And so if we have something like 13, really we're thinking about it as being positive 13. And so this is saying that it's 13 long. And in one dimension, there's really only two directions, either positive or negative. So it's 13 long and positive. So that's its magnitude and direction, versus something like minus 5. And so minus 5 is 5 long, and its direction is negative. So really, for one dimension, it's kind of boring to think about things that way. It's much more interesting to think about this in multiple directions. 2, 3 is where it's easiest to draw, but really vectors can go on and take any number of dimensions you want. So the common notation for a vector, especially if you're typing it up or printing it, is to use a bold-faced text, and so that would be capital V. And so that's usually for how I'm writing it. If I'm typing things onto the slides, I'm going to be using this boldface, and so this is in type. And this is often how things are written in textbooks. And since it's kind of hard to write boldface, it's difficult enough if you're doing this with chalk or a pencil, but on a iPad screen, it's impossible to make boldface. And so when doing handwriting, to denote a vector, we put a little arrow on top. So V with an arrow on top. So boldface V or V with an arrow, these both are going to mean the same thing. So if I'm writing on the screen, I'm going to be using the V with the arrow notation. If I've typed it in, I'm going to be using the boldface V. Okay. So the attributes of a vector are magnitude and direction. Position is not one of those attributes. Right? So if I have a vector there of a certain length in position, a certain length and direction, and I have another one, if these have the same length, so same length, and if they're pointing in the same way, so they have the same direction, so then we'd say these two are equal vectors. Okay. And so really what this means is that you can take a vector and move it around anywhere you want as long as it has the same length and the same direction. It's all the same vector. So imagine those are all the same length and all the same direction. These are all going to be considered equal vectors. So when we write a vector, so there's our vector v. You can see the handwriting notation with the little arrow on top. We can think about, when we're thinking about breaking this down, we can break it down into two parts. So a vector, it has an initial point, and that's where the vector starts at, and then it has a terminal point, and that's where the vector ends at. Okay, so as we move it around, these initial points and these terminal points can change. But if we have it fixed in any one place, then we can talk about a vector at that position, what its initial point is and what its terminal point is. So if we can move these around anywhere we want, but we want to kind of have some systematic way to talk about these, well, what makes sense, if we can put it anywhere we want, what makes sense and where to put it, well, we're going to use the origin. And so if we have a vector v and its initial point is at the origin, then we're going to say that this is in standard position. So standard position means the initial point of the vector is at the origin. Okay, so v is starting at the origin and going out to wherever it is. And so you can do this with any vector. Any vector I want, if I have some other vector w, right now that's not in standard position, but I can kind of move it over. Let's use a different color. Now you are going to be red. Imagine that's a straight line. And so now there's vector w. Same vector as before, because it's the same magnitude and same direction. I've just moved it into standard position. Okay. So once we have a vector in standard position, well, then the point, its terminal point, the point that it's pointing to, is going to be unique. Right, so let's say that it's pointing to the point x naught, y naught. Well, then the way that we can represent this vector to say that if I started in standard position, if I have its initial point at the origin, well, then it's going to go out x naught in the x direction, y naught in the y direction. And so I can write the vector like this. Notice that for the point, I'm using parentheses. But for the vector, to differentiate between the vector and the point, I'm using these angled brackets. Okay. And so what this vector v equaling x naught, y naught means is that when I have the vector in standard position, then its terminal point is at x naught, y naught. And so this x naught and the y naught, these terms here, since I'm not talking about a point, I'm talking about a vector. And so these parts, this x naught and the y naught, these are called the components of v. Okay. And the way that if I have some vector, let's call it vector w, let's say that it is -1, 4. And so we'd say its x component is -1. Its y component is 4. And what the w vector does is it moves you left -1. So starting at the origin, you move left -1. And then you go up 4. And that's what the vector does. So vector w moves you left 1 and up 4. That's its magnitude. Well, we'll get into talking about its magnitude, but it has some length that it's moved you, and it has some specific way that it's moved you. Okay, so we've been doing this in R2. We can do this just the same as in R3. And so, same as in R3, vectors, now they're moving around in 3 dimensions. We can put it in standard position. So standard position is at the origin in R3. And then if we go out x0 over y0 and then up z0, we then can talk about this vector going out to the point x0, y0, z0, and this vector v now in 3 dimensions, it's going to have 3 components. So what v does in R3 is it moves you in the x direction, x0, the y direction, y0, and in the z direction, z0. Okay, so just like you have the number 0 in numbers, we can talk about 0 vectors. And so the 0 vector is the vector where all the components are 0. So it would be 0, 0 in R2, and it would be 0, 0, 0 in R3, and we can do this in R4. It would have 4 zeros. R5 would have 5 zeros, etc., etc. And so this is the unique vector with no magnitude. And because it has no magnitude, this is the one vector it doesn't really make sense to talk about a direction with. The 0 vector doesn't really have a direction because it doesn't go anywhere. Okay, so you can kind of think about the 0 vector is the vector that doesn't move you at all. Okay, so how do we figure out the norm of a vector, what's called the magnitude of the vector? And so this is often written, you put in Stewart, you use just absolute value signs around it. And so this is sort of similar to absolute value that we have for numbers. In other books, some other common notation is to use double lines to talk about the magnitude or the norm. Either of these is fine. So what do we mean by the magnitude of a vector? Well, it's just how long it is, right? So if we're thinking about this in R2, we have our vector that's in standard position. Let's say that it goes out to what this looks roughly like 3, 2. And so this vector moves you 3 in the x direction, 2 in the y direction. So how far has it totally moved you? Well, we can create this nice right triangle, 3, 2. The length of the vector is the hypotenuse here. And so we can use distance formula, which is really the Pythagorean theorem, and say that the length of v here is going to be 9 plus 4, 3 squared plus 2 squared, and so square root of 13. Right, so in general, if we have something in 2 dimensions, v is x0, y0, then the magnitude of v is square root of x squared plus y0 squared. If we're going to do this in 3 dimensions, let's call this in 3 dimensions, let's call it W. So with 3 components, x naught, y naught, and z naught, then just like the distance formula in 3 dimensions, its length is going to be x naught squared plus y naught squared plus z naught squared. And so that's how we're going to calculate the norm of a vector, or the magnitude of a vector. Okay, so if we can have these magnitudes be of any length, then we can think about vectors whose magnitude is exactly 1. And so for a vector whose magnitude is exactly 1, we're going to call that a unit vector. So unit vectors are vectors, let's use a U, such that the length, the magnitude of U is exactly 1. And so what does that mean? Well, we have the unit circle here. Well, so if the vector is in standard position and we're doing this in R2, this means that the vector is going to point to somewhere on the unit circle. So U is going to point, if we have it starting at the origin, it's going to point exactly to some point on the unit circle. And so we can think about these unit vectors in R2 going around the unit circle in all directions. So where would they be pointing to if we were in R3? Well, it'd be pointing to somewhere on the unit sphere, which is a bit harder to draw, so I'm going to skip that here. Okay. And so there are 2 special unit vectors in R2. One is moving just in the positive x direction, and so if we go out to 1 in the x direction, we're going to call this I, and I is a vector that is just 1 in the x direction, 0 in the y direction, and you can double check. The magnitude of I is square root of 1 squared plus 0 squared, which is just the square root of 1, which is just 1. And so I is the unit vector that goes in the positive x direction. J then is going to be the unit vector that goes in the positive y direction. So J is components are 0, 1, and same as before, magnitude of J is going to be 1. Okay, and so these are the vectors that are sort of singling out going just in the x direction, then you're going along the same way as I. If you're going just in the y direction, you're going along the same way as J. So if you do 1 step in the x direction, you've gone I. 1 step in the y direction, you've gone J. We can do the same thing in 3 dimensions, but now we need a third one. So I and J are going to be the same as before. It's just now we're in 3 dimensions. So I is 1, 0, 0 in R3. J going in the y direction is 0, 1, 0. K is going in the z direction, and so it is 0, 0, 1. And you can easily double check that these are all unit vectors. Okay. And so, we're using the same notation for I and J, whether we're in R2 and R3. How do you know which one you're using? The short answer is that it really doesn't matter, because it's just saying go just in the x direction. And so long as you have at least 1 dimension, it makes sense to talk about just going in the x direction. And J is saying just go in the y direction, 1 spot. And as long as you have at least 2 dimensions, it makes sense to talk about going in the y direction, 1 spot. And K you'd only use if they were using at least 3 dimensions. And so really you know which one you're talking about just based on the context of how many dimensions you're working in. Okay, so we have some vector. Let's make that look halfway decent. Say it's V. Let's say this one is 4, 3. Well, so remember that 4 is saying that we're going out in the x direction 4. And then the 3 is saying that we're going in the y direction 3. And so V is kind of talking about a change in x and a change in y. Well, and the vector itself is sort of a portion of a line, and so it makes a lot of sense to go to talk about connections between the vectors and the slope, right? And so if you look at this vector v, so specifically it's going over 4 and going up 3, but you can notice that v is parallel, going in the same direction as lines with slope. Well, what would the slope be here? Well, the change is 3. The change in y is 3. And the change in x is 4. So it would be going along the slope 3/4. Right? And so if we had some other vector here, let's say that it's going along the same direction, but maybe its length is different. And so let's call this w. Let's say that w, let's just say its components are x naught and y naught. Well, if we know that w goes along the same line as v, if it's going along the same line, that means that its slope is also 3/4. So note that the slope of w is also 3/4. Well, then, what can we say about these components of it, x naught and y naught? Well, so on the one hand, we know v, its slope is 3/4. To get the slope from x naught and y naught, well, that would be w is telling you to go up y and over x. And so we could write it as x naught, y naught. Well, if we say we solve for this either x naught or y naught, what do we get? Well, we get that y naught is going to be 3/4 of x naught. All right, and so we can think about w then, it's x naught, y naught, which means we can think about it as being x naught and 3/4 of x naught, or so what exactly is this saying? Well, it's saying that the ratio between the first term and the second term is going to be 3/4, no matter what, right? And so, in fact, if we set, let's set x naught, since the y variable has, since we have a 4 in the denominator there, let's kind of cancel that off. And so let's set x naught to be 4L. Then what's y naught going to be? Well, y naught is 3/4 x naught. And so if we replace that with x naught with 4L, we're going to have 3/4 times 4L. And so the 4's cancel. We're going to have it be 3L. And so what's w going to look like? Well, it's going to look like 4L comma 3L. Well, 4L comma 3L, how is that different than our original vector v, which is 4, 3? Well, we're just multiplying each component by the same amount, by this amount L. And so what does this mean? So if two vectors are on the same slope, the components are going to be sort of a multiple. Each component is going to be sort of a fixed multiple of the original vector. So in all of this, we've been doing this with L being positive because things are going in the same way. This line goes both directions, so what happens if W is pointed the other way? So let's clear up some space here. Come on, clear them out more. So got a little bit of space at least. So we had this V, let's use blue for V again. So let's say we had V going off in this direction. Let's say that it's still 4, 3, but now we have W going in that direction along the same line. Well, W, we can do the same thing as before. The slope is still going to be the same. It's just now they're going to be negative multiples of V. So it's still going to be look like 4L, 3L for some L, but now L is going to be negative. Okay. Okay, so how do you tell if you're given two vectors, you're given the components of two vectors. So let's say we have V is A comma B, W, let's say that it's C comma D. How can you tell if V and W are along the same line? Well, from what we saw before, V and W are on the same line if the components of V, so the slope of V is equal to the slope of W. So you can think about this as talking about the slope of V. And this is talking about the slope of W. So if that's true, then they're on the same line. So that means that either they're pointing in the same way or they're pointing in exactly opposite ways. How do you tell whether they're the same or the opposite? Well, if this is true, if A and C have the same sign, and A and C, the same will be true with B and D, then they're going in the same direction. If A and C have opposite signs, even though my handwriting is not fantastic, at least I could spell it correctly. If opposite signs, then we're talking about opposite direction. Okay, so have two vectors, you calculate their slopes. If their slopes are the same, then they're either going in exactly the same direction or exactly the opposite direction. If they have the same slope, then you just pick one component, either the x component or the y component. Look at the signs of those components. If they're the same sign, then they are going in the same direction. If they're opposite signs, then they're going in the opposite direction. So let's do quick example with actual numbers. Okay, so if we have minus 1, 2, so going minus 1 in the x direction, plus 2 in the y direction, versus minus 4, 8, right? The slope of both of these is both negative 2. The x components are both negative, and so these are in the same direction. On the other hand, if we did, let's clear out some more space. I don't know why this eraser is being so poor right now. If we did minus 1, 2 versus 3 minus 6, so we calculate the slope here, we get minus 2 again, but now the first one has the x component's positive, and the second one the x component's negative, and so these are in opposite directions. And let's do one more, just because this is kind of fun to do it with actual numbers rather than just variables. Let's do minus 1, 2 versus 7, 5. In this one, they have different slopes, and so different slopes mean they lie on different lines, and so these are just different directions. Completely different directions. Okay, so now we talk about things, talking about vectors being in the same direction or opposite direction. In that case, they're going along the same line, and so they're parallel to each other. Well, if we have parallel, then we can also talk about perpendicular. And so the fancy math name for perpendicular, even fancier than perpendicular, is what we call orthogonal. So orthogonal means that it's going perpendicular to two things. If two things are orthogonal, they are going perpendicular to each other. They're going at a 90-degree angle to each other. And so to figure out what vectors like this are going to look like, let's go back and think about two lines. And so let's say we have this line L. Let's say that its slope is, this one looks like it's roughly, let's say 3/2. And so that means anytime that I go over 2, I'm going up 3. So if I wanted to do the line that's perpendicular to L, and so that looks roughly perpendicular to L. Let's call this line fancy script K. Well, then what's the slope of K? Well, the trick to get perpendicular slopes, if L and K are perpendicular, that means that the slope of K is the negative reciprocal of L. And so the slope of K in this case is going to be minus 2/3. You can kind of see that here, that if I go to the left minus 3 and up 2, that's going to give me K. Okay, well, so then how does that correspond to vectors? Oh, there's my big eraser. Much better. Well, so let's say then I have my vector v. Let's say that it is 2, 3, and I want to make a vector perpendicular to it. So let's find some vector w which is perpendicular to v. Well, that means that I want the slope of w to be the negative reciprocal of v. And so the easiest way to do that is to swap the two components and make one of them negative. And so for this, I can choose w to say, I'm going to swap 2 and 3, so it's going to be 3, 2, and I want to make one of them negative. And so let's make the first one negative. So w is going to be minus 3, 2. And so if we want to do it the other way, minus 3, 2, there's going to be w. And you can see they look like they're at a right angle to each other. And so this is a cheap way to get two vectors that are perpendicular to each other. Swap the components. So let's write this out. Swap components and make one negative. So this is how you get orthogonal vectors in R2. R3, it's a bit more complicated. We will talk about getting orthogonal vectors in R3. One of the things that makes it much more difficult in R3 is that in R2, if you want, if this is happening on a plane, you want something at a right angle to it, there's only two ways to write that right angle. It's either going to go in the direction of w, or it's going to be negative that, going in the direction of negative w. Whereas if we're doing this in R3, well, if you have some vector v, and then you talk about a right angle to it, you actually can swing that right angle around in a circle. And so there's not just two directions that are orthogonal to it. There's actually a full circle of directions orthogonal to it. And so unless you're going to talk about one specific way, it makes it a lot more, there's a whole lot of flexibility there. Okay, so last thing, talking about vectors, got back here the unit circles. So we've been talking about them being, vectors have magnitude and direction. Really, we've been focusing in on breaking them down into x components and y components, but that's not the only way to think about them. And in fact, in physics, they use vectors a lot, and often, much more in physics, they might be thinking about things in terms of length and angle. And so if I have some vector v, right? So the way that we've been thinking about it so far is if it's pointing to the point x naught, y naught, then we talk about v as having components x naught and y naught. If we want to think about this as in terms of magnitude and direction, well, the magnitude is the length. And so we can say this length here is r. And so r here is talking about the length of v. And then to talk about an angle, well, we're going to pick, like going up from the x-axis, same as we always do for angles in radians. So we'll call that angle theta. And so we can think about v also as being a vector of length r with angle, and so we're always talking about the angle is going up from the positive x-axis, theta. So what does that mean about x naught and y naught then? Well, if we use this, our Pythagorean theorem, our hypotenuse now is not 1 because we're outside the unit circle. Our hypotenuse is r, the length of this. And then the sides are going to be coming from multiples of sine and cosine. And so our x naught here is going to be talking about the bottom side. And so the hypotenuse is r. And so then the base would be r times cosine theta. And y naught is going to be r sine theta. And so anytime you're talking about a vector of a particular length and angle, and you want to write that into its components, this is the formula you're going to use. The x component is going to be r cosine the angle. The y component is going to be r sine the angle. If you're going the other way, well, if you're given x naught, y naught, and you want to go to r and theta, well, r is easy enough. That's the length. And so it's going to be x naught squared plus y naught squared. How can we get that angle there? Well, the angle, we're going to have to use the fact that the slope, y naught over x naught, is going to be equal to the tangent of this angle. And so if we want to solve for theta there, theta is going to be the arctan of y naught x naught. Okay, that's all I have for you for this video. I will see you later.